In this lecture, we're going to examine the idea of electric power. It says concentrated power is not rendered harmless by the good intention of those who create it. Now, that's a famous quote by the famous economist Milton Friedman. So let's take a look. It says that the goals are that you be able to calculate electric power, given voltage, current, resistance, those sorts of things. And that you understand the origins of the different power equations. There's actually 3 different equations that allow you to solve for electric power, but really, in essence, they're the same one equation. You should also be able to understand the relationship between power and energy. Now, we've talked about the idea of power and energy earlier this year, and we said that power is the rate at which energy is used. And we're going to re-examine that in terms of electricity. You need to be able to understand the law of conservation of energy, and you need to be able to determine factors that can reduce your utility bill. So, first off, what we already know. We already know that power is the rate at which energy is used. We've used this expression earlier this year, and we said that you can pick up a heavy box very quickly, or you can pick up a heavy box very slowly. The amount of work that's done is the same, but what is different is the power, because the time in which you're doing the work or changes. So work really can be any sort of energy. That's the idea of the conservation of energy. You can say that work is equal to kinetic energy for a particular set of circumstances, or you can say that it equals gravitational potential energy for a certain set of circumstances. So, in the lab, we learned that increasing the voltage increased the brightness of the bulb. Now, whenever we're talking about the brightness of the bulb, what we can say is that as the brightness of the bulb increases, then you're putting out more energy every second. So in other words, by increasing the brightness of the bulb, you've increased the power. Now, we also learned that increasing the current increases the brightness of the bulb. So if we look at our units, how can we get the units from electric units to units of power? Now, remember, a unit of power is 1 watt, which is the same thing as 1 joule per second. Now, we already studied the amp and the volt, and we said that 1 is 1 coulomb per second, and that's an amp, and we know that 1 volt is 1 joule per coulomb. If you take a look at these units, if you were to multiply these two units together, 1 joule per coulomb times 1 coulomb per second, the coulomb term is going to cancel out of both of them. And what you're left with is 1 joule per second, which is the same thing as a watt. And that is the origin of our equation that we have here, which is the electric power equation. And the electric power equation is that electric power is equal to the current times the voltage. So this is very similar to we've talked about all of these variables in detail before, so there's really nothing new here. Whenever we're talking about P in this instance, we're talking about electric power, but really it's no different from power we talked about earlier this year. So let's take a look at some examples. This first one is a very complicated example. It says, what is the rate at which a light bulb uses energy if 50 millimoles of electrons move down a wire per hour? A single electron contains 1 times 10 to the minus 12th joules of energy. Now, if you were to look at this, you have the idea that P equals IV. Okay, that's the overall equation that we're going to take a look at. But unfortunately, I don't have current. So what you can do is you can actually solve for the current using the equation NE over T. That's what we used earlier when we talked about electric current. The number of electrons times a constant divided by time gives you the current value. Now that we can do the same thing for voltage. Okay, remember voltage is the energy per charge. So I can say how much energy divided by the charge. I'm going to say EPE. Okay, divided by the charge. And if you look at that, you can take these things and you can combine them and you can get basically what you're looking for. So if you were to look at it, you have this right here is a single electron. This right here is the charge of a single electron. So because of that, these two values are going to cancel out. And what you have now is just the N term times the joules, which is 1 times 10 to the minus 12th, divided by the time, which is going to be 3600, because it tells it to me in hours and I want it in seconds. So now the only thing that's left to do is to figure out what this N term is. Now we have 50 millimoles of electrons. So you have 50 millimoles of electrons. Well, there are 1,000 millimoles in 1 mole. And then so you have your value of 0.05. We move it over 1, 2, 3, 0.05 moles. Now remember that a mole of anything is an Avogadro's number, which is 6.02 times 10 to the 23rd. So what I need to do is I take these two values and I multiply them, or I substitute them in for n. Once I've done that, now I have everything that I need to solve for this particular value. And when you plug all your values in, you end up with an exceptionally large number. And that number ends up being about 3 times 10 to the 11th watts. 10 to the 11th watts, which is a very, very, very large number for power. In the next example, it says you have a 1,000 megawatt laser that is produced by a 180 amp millicurrent. Okay, capital M stands for mega, which is times 10 to the 6th. Lowercase m stands for milli, which means times 10 to the minus 3rd. So if you look right here, it says what is the voltage responsible for producing this current? So I want to use the equation P equals IV, and I have an exceptionally large current value. This ends up being 1 times 10 to the 9th once you take 1,000 and multiply it by 10 to the 6th. Equals, the current on the other side is milliamps, so I move it over 1, 2, 3, and I get 0.18 amps. That allows me to solve for the voltage, divide both sides by 0.18, and whenever you do that, you end up with a voltage value of about 5.56 times 10 to the 6th volts. So an exceptionally large voltage. The third example, we actually take a look at a circuit. It says that a circuit is built in which a 9-volt battery is connected to a 100 ohm resistor as shown below. When the switch is closed, what is the power dissipated by the circuit? So we're assuming that we close this thing. Now what we can do is we can use what we've already learned, Ohm's law. And when we use Ohm's law, we can say that 9 equals I times 100, or that I equals 0.09 amps. Once you've established what the current value is, you can then solve for the power. Power is equal to current times voltage. Or in our case, it would be 0.09 times 9, which would end up giving us a value of about 0.81 watts. Two light bulbs are lit below. Which light bulb has a higher wattage? And I can tell you that this right here is a trick question. Okay, now if the two light bulbs are the same type of light bulb, in other words, they are both incandescent or traditional light bulbs, or if they're both LED light bulbs, or if they're both CFL light bulbs, which are those kind of ones that curl, then you can compare them directly. You would say the one that is brighter is the one that uses up or has the higher wattage. But you can't say that if they're not the same. For example, if this one right here is an LED, which stands for light emitting diode, it could be like a 3-watt LED. If you were to compare that to this, which could be a traditional incandescent, this right here could be a 60-watt bulb. So the brightness of a bulb is only related to the energy if they are the same type of bulb. So make sure that you check that before you move on. It says, when current can't be measured. Okay, there are certain circumstances in which current is difficult to measure. If you can't insert an ammeter into an existing circuit because either you can't get it into the circuit itself, or there's some sort of high voltage situation where you can't directly measure the current, but you still want to know the power, we can take the Ohm's law equation and the power equation and we can combine them. What I want to do is I want to solve for I. So I say that I is equal to V divided by R. Okay, that's just a rearrangement of Ohm's law. But now I have an equation for I. I say I equals V divided by R. I can now take that and I can substitute it in for I in the other equation. When I do that, I get P equals V over R, which is what I had that was equal to I, times V. When you simplify that, you get the equation P equals V squared over R. This is another equation that you can use to calculate electric power. Now, this equation is really just a combination of two equations that you already know. If you are more comfortable solving for I and then plugging it in and solving for P, like we did in this example, up here, if you want to solve for I, plug it in, and then solve for P, feel free to. That's up to you. There's no problems with that whatsoever. But you can simplify it in this manner. Now, when you have a 60-watt light bulb, that is plugged into a 120 volt American outlet, what is the resistance of the particular light bulb? So this is an instance in which I'm trying to solve for the resistance. I have the power, so my traditional power equation isn't going to work, that I can actually use the other equation and solve for it. If I were to use the equation P equals V squared over R, I can easily solve for this. I would say that 60 equals 120 squared divided by R, multiply both sides by R, divide both sides by 60, and when you do that, you get a resistance value of about 240 ohms. Electrical power is the same thing as mechanical power. You can use electricity to do physical work, and you can do physical work in order to generate electricity. There will be more on that when we talk about it in terms of electromagnetism. But basically, these two equations are the same. So because of that, a lot of times you can relate these two equations using this particular term right here, where any sort of energy divided by time is equal to the current times the voltage. An example of that is this. It says how fast, and then it says constant velocity, that's kind of a key. Can a 9-volt battery pick up a 100 kilogram person if exposed to a safe current of 1 amp? Okay, so you are picking up a person and you are doing work on them, lifting them off the ground. So what I can say is that I have two power equations. The first one would be that I have some sort of work divided by time. And on the other one, I have a current times a voltage. Now I have the voltage and I have the current. And if you look at this, there is some other information that I have here, but there's nothing that stands out as far as what I'm trying to get done. So what I'm going to do is I'm going to expand the equation for work like we did when we talked about energy. So I'm going to say that that is force times distance over time. Okay? And if you were to look here, you can simplify this distance over time term to be force times velocity. That is equal to current times voltage. Now this is a lowercase v and this is a capital V, just to keep those straight. So if you were to look at this, I'm starting to get there because the term how fast, now I have a term that expresses how fast. The problem is that I don't have a force value, except for the fact that you realize that you are picking this person up against gravity. So the force that you're picking them up with has to at least be equal to the gravitational force. And you have a mass, which allows you to calculate the gravitational force. So another way of expressing this term, we're going to change colors just to kind of highlight it, would be mass times gravity times velocity is equal to current times voltage. Now I can plug my values in. 100 times 9.8 V is equal to 9 times 1. Take both sides, divide it by 980, which is what you get when you multiply 100 times 9.8. And when you do that, you actually get a very, very, very small velocity value of 0.0092 meters per second. Now what you should realize is, people say, well, that's a really slow velocity. That's like 9 millimeters. That's not even 1 centimeter per second. And that should make sense because you are using a 9-volt battery to pick up a 220-pound person off the ground and move them into the air, which is pretty unrealistic. So we would expect to have a reasonably small velocity like we do. Okay, now we introduce the idea of electric energy. Now, electric energy is the same thing as energy that we've been talking about. It is the amount of energy that an appliance uses. The most common expression that you have for electric energy is taking power and multiplying it by time. Now, that's basically the same thing that we've been talking about. You take power times time and you solve for energy. It's a rearrangement of the equation E equals P over T. Oh, excuse me, yeah, P equals E over T. It's a rearrangement of that. Now, this right here is what you get monthly. It's called an electricity bill if you haven't seen one before. And what it does is it actually tells you how much energy you use. Now, a lot of times it has a misnomer. It's called the power company or the power bill, but it's not. It's the electricity bill. And if it tells you right here, it tells you your total electricity usage. And your total electricity usage is actually measured in something called the kilowatt hour. Now, the reason why you have something in the kilowatt hour instead of the joule is that, remember, the joule is an incredibly small unit of energy. And whenever we're talking about the electricity that's delivered to your house, we need a very large number. If you were to talk about joules, you'd get a bill that would be, you use 74 trillion joules of energy in a particular month. And it doesn't make any sense to talk about it in terms of those numbers. So instead they use the kilowatt hour. Now, the kilowatt hour is a much, much larger unit of electricity, or excuse me, of energy, but it's easy to convert back and forth between them. Okay, so for example, a joule is what you get when you multiply 1 watt times 1 second. So you can figure out what you've got going on here if you look at it in terms of a kilowatt hour. Well, a kilowatt hour is equal to 1,000 watts. Okay, that's the whole idea right there. 1,000 watts times 3,600 seconds, because that's how many you have in an hour. When you multiply those two values together, you get something like 3.6 times 10 to the 6th joules. That's how much energy is in one particular kilowatt. So if you were to look at your electricity bill and you have something like 2,500 kilowatt hours, you would have to multiply that number by 3.6 million to get the number in joules. It's a pretty unrealistic number to work with. But we have E equals P times T. We have talked about everything in relation to each one of these variables, so there is nothing new here. So now what we want to do is we want to go ahead and take a look at an example question. And in this example question, it says you have a 500 megawatts of electric power is supplied by a turbine. It says the turbine is 75% efficient. What is the mass to time ratio for water falling if it falls from a height of 34 meters? So what it's saying is that you have water that's coming over the edge of a cliff. It's used to turn a turbine, which is used to make electricity. Now, of the energy that is made here, only 75% of it gets turned into electricity here. And it tells you that of this, you have 500 megawatts that is produced. So it wants to know how much mass of water you get every second. That's the mass to time ratio that you're looking for here. So we're looking at it in terms of power. So if you were to look at it in terms of power, you have power is equal to energy divided by time. Now, when we're looking at energy in this particular case, you're talking about water that is falling over the edge of a cliff. That makes it gravitational potential energy. So I'm going to rewrite this expression as power is equal to mass times gravity times height divided by time. And that's a common expression that we have. So now once you are here, you realize that I'm trying to solve for the mass to time ratio. Well, that is these two things combined right there. That's the mass to time ratio. So what I can say is that m over t is equal to P divided by GH. Now if you look, I have a power, but this is not the power that I am supposed to use. Remember, that is how much electricity is generated after a 75% efficient conversion at this point, conversion from mechanical energy to electrical energy. So you have to take that into account, that only 75% of it is produced. So you can take this thing right here and you can divide it by that 0.75 value. When you do that, you can now plug that number in for the power. And you also have the number for gravity, that's still 9.8, and you have the height, that's 34. When you finish plugging all those numbers in, you should get a mass to time ratio of about 2.0 times 10 to the 8th, to the 6th kilograms per second, which means that you have about 2 million kilograms worth of water that flow over the edge of this cliff every second, which is quite a lot of water. In the next example, it says determine the amount of energy that a battery had if a 9-volt battery can provide energy to a 5 ohm resistor for 8 hours. So in this particular case, we have to combine multiple formulas. We are trying to solve for the energy of a battery. Energy is equal to power times time. Now, unfortunately, I'm not given the power, although I am given the time. So what I can do is I can say, okay, well, what do I have for power? I have the voltage and I have the resistance. So what I can do is I can substitute one of my equations in there. And the equation that I'm going to use in this particular case is V squared over R, because I have voltage and because I have resistance. And then I can multiply it by time. So when I take a look at this, I would say that 9 squared divided by 5 times 8 hours, but remember, you've got to convert 8 hours into seconds at this point if you're trying to get it into joules, and so that would be 8 times 3600, and that would give you a pretty large value of about 4.66 times 10 to the 5th joules. Now, the next one is example D3. It says that a battery is rated for 240 amp hours. So look at the units right there, amp hours. Well, remember that 240 amp hours, remember an amp is a coulomb per second. So when you multiply this, what you're really telling me is what the charge value is, because you're taking amp hours and multiplying it by 3600 seconds, and that right there tells you the Q value, or the charge of a particular battery. Okay, so let's look at it in terms of the equation. I'm trying to figure out what the total energy capacity of the battery is, or E equals P times T. Well, when you do this, you can actually put in the equation IV times T. And that really doesn't mean a lot to a whole lot of people, but I'm going to write it this way: IT times V. And when you do that, you should recognize that that's what this is. You're taking amps and you're multiplying it by time. So the 240 number represents these two values combined, which is also known as the charge. So this 240 times 3600 times 12 is the total energy capacity of a particular battery. So that is about 1.04 times 10 to the 7th joules. In the next example, it says, determine the energy used by a 100-watt light bulb in 5 minutes. So we're going to do energy is equal to power over time. We can convert the time from 5 minutes into 300 seconds. And we have it equals 100 watts. So if we're trying to solve for the total energy, sorry, we wrote this down wrong. It's power equals energy over time. Okay, we multiply these two values together and we end up with 300 times 100 equals E. And when you do that, you end up with about 30,000 watts, joules of energy. The last part of this video wants to take a look at the cost of electrical equipment, or of electric power. So, in order to figure out the cost for an electricity bill, the total amount of money that you spend on electricity is equal to two factors: the energy that you use and the rate at which you are paying. Okay, so the energy is something that you can control. The easiest thing to do is turn off lights, adjust your temperature upwards on your air conditioning or lower on your heater, depending on the season, and then also unplug your electrical devices. Now, even your chargers that are plugged in with no phone attached to them, or your screens that are turned off but are plugged in, or your computer or your washer or dryer, they are still using a small amount of electricity. So one way you can reduce your total consumption is to unplug devices themselves. The other thing that you can do is you can actually adjust your rate. Now, Texas is a um, power to choose state in the sense that you have the right to choose your own electricity company. And when you do that, whenever you choose your own electricity company, you are offered a variety of rates. You can go for a very cheap rate, which a lot of people do, or you can choose to pay a higher rate if you are looking for something that is more environmentally responsible at that point. And that is entirely up to you. But that number right there is your rate. Generally speaking, the energy is expressed in kilowatt hours, even though, yes, I know the standard unit is the joule. So the rate that you see is usually seen as dollars per kilowatt hour. Now, generally a reasonable rate for electricity, it varies depending on the year and it varies depending on the season, but is anywhere between 8 cents per kilowatt hour to about 18 cents per kilowatt hour. And that depends. If you were getting 18 cents per kilowatt hour, really what that means is you're using almost entirely all green renewable resources as your electricity provider. So, example E1. The Xbox One has two inactive power modes. The first, Instant On, uses 15 watts, while the second, Energy Saving Power Mode, uses zero point 0.5 watts. How long must your Xbox be in energy saving power mode to save you $1 on your electricity bill? This is the cost of electricity is about 10 cents. So this is one of the things that's interesting because you can see whether or not it's worth it to turn off this particular device. So, the first thing that you need to know is that we are trying to solve for the money, how much money that it takes. I need to know two things. I need to know the energy and I need to know the rate. This number right here represents the rate. This number here represents the total amount of money that I want to save. So I have $1 is equal to the energy times the rate. Now the problem is I'm not particularly interested in the energy. I want to know how long it takes for the Xbox One to be on. So if you were to look at energy, and instead of writing energy, if you would have put the expression power times time, that's a whole lot more helpful because now I have the time factor. The only thing that you need to know now is the power factor, and there are actually two powers for you to look at. Now remember, the first one, Instant On, uses 15 watts, so by switching to the energy saving power mode, you actually save 14.5 watts. Now remember, these things right here are in kilowatt hours and dollars per kilowatt hour. So you need to make sure this power is in kilowatts. So what I need to do is I would divide it by 1,000 or move the decimal over 3. So my power would be 0.0145 kilowatts. And then I would multiply that by the times in there. That's the power times time expression. And that allows me to solve for the time. So the first thing that you would do is you would multiply 0.0145 and 0.1 together. And whenever you do that, you would divide both sides by that number. And so this ends up being about 700, when you solve for the time, it's about 714.3 hours, which means it's roughly about 30 days. So in 1 month's time, you'd save about 30 days by having it on the power saving mode as opposed to the instant on. So you need to think about it. You say, okay, is it worth it for me to have instant on for an extra dollar a month? And you can make that decision depending on your circumstances. The next one says a house uses an average of 2,000 kilowatts of electricity per month. How much can you save on electricity by switching electricity providers and lowering your rate from 16 cents per kilowatt hour to 9 cents per kilowatt hour? So in here, we're once again looking at the cost of electricity. Now in this case, we're going to leave the total energy consumption constant. So what we want to know is we want to know how much we can save. So you can agree that if I were to switch electricity providers, I would save 7 cents per kilowatt hour that I use. Okay, that's just how much I would save. So I'm going to enter this number, my savings number, in as my rate. When I do that, I take 2,000 and I multiply it by 0.07. And whenever I do that, I end up with a value of about $14. Now, $14 a month, you multiply that by 12, you're starting to look at something along the order of like $168 a year, which may be worth it, it may be not, it's up to you. It's one of those things where this might be from renewable resources and this might be from something like natural gas or coal, and you would have to make that decision as far as what you decide to use.